A common series that you might encounter is what's called a telescoping series. So what ends up happening in a telescoping series is that you have terms, and each time you generate a new partial sum, you keep canceling out pieces from the previous partial sum. And if that keeps happening, if you can sort of guarantee that that's going to happen, then you can rewrite the sum in a very particular way and solve it. So it's kind of convenient. And I'll show you what I'm talking about. So we say that it's telescoping if successive terms always cancel out previous ones. A simple example is this: 1 over n minus 1 over n plus 1. So if I look at the first term of this sequence, not of the partial sum, but just of this sequence, it's 1 minus 1/2, right? If I plug in n equals 1, I get 1 over 2. Now the second term, when n is 2, it's 1/2 minus 1/3. And the third one is 1/3 minus 1/4. So if I start looking at these partial sums, all right, the first partial sum is 1 minus 1/2. The second one is 1 minus 1/2, and then 1/2 minus 1/3. So this cancels. In the third partial sum, I get 1 minus 1/2, 1/2 minus 1/3, so that cancels. And then I get 1/3 minus 1/4, so that cancels. So in the first term I have 1 minus 1/2. In the second term I have 1 minus 1/3. In the third term I have 1 minus 1/4. So it might be reasonable to conclude that the nth partial sum is 1 minus 1 over n plus 1. Whoops, that's 1 over n plus 1. And there are techniques that allow us to determine that that's actually true or justify that statement. But for our purposes, if you can find that pattern, that'll be sufficient. But if I have this pattern, if this is the sequence of partial sums, what happens is I take n to infinity. Well, that doesn't go away, right? That's just a 1. It doesn't depend on n. But as n gets really large, 1 over n plus 1 drives down to 0. So since this drives down to 0, we know that the limit of the partial sums is equal to 1. And therefore, the sum of this entire series is 1, which is kind of neat. It allows us to not, if you were to like put this together and like into a single fraction, it would be kind of gross, and it'd be hard to realize if it is going to converge or if it isn't going to converge. You know, you may not know off the top of your head, but this is easy to understand. Now, the problem is that telescoping series a lot of times creep up on us. And by that, what I'm saying is they don't just say, oh, I'm a telescoping series. Like, this kind of advertises it, because if you look at this and that, this is lagging behind that term, right? It'll get there in the next sequence, right? It starts at 1, this is 1/2, it's the other way around. This is lagging behind that. You know, in the next term, this is 1 ahead, so it's always, it's going to be chasing it. But that may not be readily apparent when you look at something like this: 18 over 9n squared plus 3n minus 2. That just looks nasty, right? If you were to simply plot out the partial sums and plot out the sequence terms, it may not be readily apparent what the pattern is. But if we do partial fraction decomposition, which I hope you are familiar with now from our discussion in it in previous sections, you can get that this decomposes into that. And hopefully you can actually multiply through and verify. That's actually pretty easy to verify. Well, anyway, I'll keep going. But it decomposes into this. Now, this looks like a telescoping series. Why does it look like a telescoping series? It looks like a telescoping series because the numerators are the same and the denominators just look like offsets. If the denominators look like offsets from each other, there's a good chance that it's a telescoping series. Notice that this is only 3 different than that. Okay, it may not be, but it's a good indication that we're looking at telescoping series. So if I generate the first 3 terms, I get 3 minus 6/5. Then I get 6/5 minus 3/4. So those match, but they're opposite signs. And then I get 3/4 minus 6/11. Okay, so if I keep going through this, I have 3 minus 6/5 for a partial sum. And then I have 3 minus 6/5 and 6/5 minus 3/4. So those cancel. And then I have the same thing here. So cancel, cancel, 6/11. Now if I pull those terms out and I factor kind of conveniently, if I pull like a 3 out, I get 1 minus 2/5. Then I get 1 minus 1/4. Then 1 minus 2 over 11. So what I'm seeing is that it's 1 minus something, and that something is shrinking. But shrinking isn't enough. You need to be a little more explicit. How can I write this in terms of these? Well, it actually turns out that it's just 3 minus, or 1 minus 2 over 3 and plus 2. Another way to write this, and maybe you'll like this better, would be 3 minus 6, 3 and plus 2. And the reason I say you might like that better is because then it's just that term. It's just that nth term. So all I really have to do when I take n to infinity is look at this fraction. Well, clearly as n gets large, that fraction shrinks to 0. So what we find is that the limit of the partial sums goes to 3. So the sum of the convergent series is 3. So it's a really kind of a convenient way to deal with this. There are other techniques that you'll learn later, and you will want to apply those techniques to solve something like this. And it is possible to do that. But if you write it as a telescoping series, you can get to the result a lot more quickly and a lot more straightforwardly than trying to apply like what we're going to do with like an integral test and stuff like that. That's way overkill for what you're trying to do. So put this tool in your kit because it's useful to have when it shows up.